So what we did last time, we had just introduced doing double integrals. These are things that look like this. And we looked in example 1.8. We had when R was a rectangle. Well, so the easiest case to deal with is when the region R of integration is a rectangle that's aligned with the coordinate axes, meaning the sides of the rectangle are in parallel to the coordinate axes. This is the x-axis, and this is the y-axis. Then this kind of thing became the integral from c to d of the integral from a to b of f of xy dx and then dy. So the double integral, which was up here, became a repeated integral. So just some of the terminology. This thing is a double integral. The original thing. This representation we're looking at here is more what you'd call a repeated integral. Because it's one integral and then a second integral. Okay? Or it's a series of nested integrals, one integral inside the other. So an example of one of these was example 1.8, which we did last time. And in section, I mean, if you missed the last lecture, do look over the video recording of it, where we talked very carefully about the meaning of these and how the meaning of the individual integrals related to the meaning of the double integral, which was the volume lying over the base plane and bounded by the surface on the other side in the kind of cylindrical region over R. Now sometimes, so just a couple of evaluation techniques in section 1.15, sometimes our functions will be separable. Separable is a word that comes up a lot as a technical term in mathematics. In this context here, what we mean is that our function, which is a function of the two variables f of x, y, can be separated so that the dependence on x and y are separated into two different terms, two different functions that multiply together to give the function f. Okay? So sometimes separable functions of two variables is a special class of functions. Those functions where you can separate out the dependence on x and the dependence on y and have a function of x times a function of y. So for example, e.g., like f of xy equal to x squared y, or what's one of the coursework? Oh, it's x times y times tangent or something, isn't it?
Tangent.
Well, let's just say it was this one. This one you can completely separate out the dependence on x from the dependence on y. So that is a g of x times a h of y, where g of x is x squared and h of y is y times the tangent of y. So that would be an example of a separable function. Something which would not be separable, whereas like f of xy equal to the cosine of x times y. Well, there's no easy way, or there's no kind of simple way that we can separate out the dependence on x and the dependence on y into two separate functions and have them multiply each other to give f.
It's impossible to separate them out. Or
Yeah.
It's not easy.
Well, I'm saying it's probably, I mean, I can't think of a way to do it. But, you know, careful as I am, I won't claim that it's impossible. But it's probably, you know, no, it's certainly not possible to do it where you've got nice continuous functions of the x and the y. Integrals. But anyway, so what the remark we want to make is that for such functions, for separable functions, their integrals separate as well. So if you have the integral from a to b, or c to d, of f of xy dx dy, you see, once you change the representation of the function into its separated form, g of x multiplied by h of y dx dy, these things can start to move around, okay? Because the inner integral, and this is one integral inside another, the inner integral is integrating with respect to the x variable. So just as in partial differentiation, in partial integration, when you're integrating with respect to the x variable, the y variable is treated as a constant. Their integrals separate also. So to do the integral inside the red brackets here, we're integrating with respect to the x variable. So any y's we see are treated as constants for the purposes of this integration. So this factor here, h of y, it just acts like a big constant. And of course, integration is a linear operation, so that constant h of y can slide outside. And it multiplies the integral. So the h of y slides outside because it has no dependence on x, and we're left with the integral from a to b g of x dx. And this is currently inside the y integral. But of course, this is just going to be a number. It's a definite integral of a function of one variable x, integrating the x variable from a lower limit to an upper limit. So this is just going to come out to be some number. It certainly has no dependence on the y variable. Okay, it's some kind of fixed value, but it doesn't depend on the y variable. So no dependence on y. So as far as the y integral is concerned, this is just like a big constant sitting inside the integral. So it itself can slide outside the y integral. So then we've just got the integral from c to d of h of y dy. Separately, the integral from a to b, g of x dx. So you got the two integrals separated, each doing their own integral, and then multiply together the results. So for separable functions, they're double integrals, at least over rectangular regions like this, also separate. Another thing we can do is change the order of integration. So our integral c to d of the integral a to b of a function f of xy dx dy, we can also say that this is equal to integrating a to b of the integral c to d of f of xy dy dx. Okay. So on the left-hand side, the inner integral is the x integral, whereas on the right-hand side, The inner integral is the y integral. Okay? So we simply swap the order of integration. So now on the right-hand side, the y integral is performed first, and the x integral second. So let's look at an example of doing that. The reason we remark upon this is sometimes changing the order of integration can be used to simplify the integration process. Okay? So this can simplify the evaluation. Sometimes. Okay. Sometimes it may be advantageous to integrate the function first with x and then with y, or vice versa. So let's consider this integral here in example 1.19. So this integral I is the integral 0 to 1 of the integral 0.2 to 0.8 of x times the cosine of xy dx dy. So this is an integral over a rectangular region for sure. It's 0 to 1 on the y and 0.2 to 0.8 on the x-axis. Okay, so it's this region of that's the region of integration there. Now, as it stands, to evaluate this, we would have to evaluate the x integral first, because it's the one on the inside. It's the one that's available for evaluation directly. But the function that we have to integrate is a product of two functions of x. It's an x times a cosine of x times y. So this integral looks slightly awkward. It would require at least integration by parts. Remember, when you're differentiating a product of two functions, use the product rule. If you want to integrate a product of two functions, the product rule in reverse is really integration by parts. And if at all possible, our life would be easier if we didn't have to do integration by parts, if we could just use simpler integration principles or simpler results. And that can be achieved by reversing the order of integration. So if we choose to do the y integral first, and only after that has been evaluated to perform the x integral, then it looks a bit easier. So if the x integral remains as it is on the outside, and if we perform the inner integral, this function has a much simpler y integral. Okay, it's basically just the sine of x times y. Sorry, it's basically just the cosine of x times y. So that will integrate to the sine of x times y divided by x, and then you've got that factor x there. So it just integrates to sine of xy. So we're able to achieve that first integral without using anything. Integration by parts isn't that complicated, but certainly good when you don't have to do it. Now remember, these limits of integration, these came from the y integral. So these are limits for the y variable. So when we substitute these back in,
Did you not want to write x as it is?
this x here in front?
Yeah.
No, but it gets cancelled out, because if you think about differentiating this with respect to y to go backwards, it'll be cosine of x times y multiplied by the derivative of this with respect to y, which will be x multiplied by x. So that gives you the x there. No, but if you take this and differentiate it with respect to y, you get this. If you like, I could have kept the x here, but then I'd need then to integrate just the cosine part on its own, it'd be sine xy over x. So the x and the x are kind of cancelling. And when you do the evaluation, this just becomes, so the top evaluation at y equals 1 is sine of x, minus the bottom evaluation at y equals 0, but that's just minus sine of 0, which is already 0, so that won't contribute. So the integral reduces to this, and that just looks like a plain old integral of a function of a single variable, whose integral is minus the cosine of x, evaluated at 0.2 and 0.8, which is whatever it is. I haven't evaluated that for some reason. But that's just the straight difference of these two values of cosine. So the change of order of integration has made the integration easier. Okay? So it's available to us as an integration technique. And in the case of when the region of integration is a rectangle aligned with the coordinate axes, it is as easy as just picking up the two integration operations and flipping them. Okay? Whereas you must remember the 0.2 and 0.8 are the limits on the x-axis, the 0, 1 are the limits on the y-axis. You can't interchange those. These have to stay x limits, these have to stay y limits. So you pick up the two integration operations and just flip them. But now, so far we've just looked at this very simplest case of a double integral, which is where the region of integration is kind of as simple as it can be. Just a rectangle parallel to the x and y axes. Okay? And not all regions look like that. Okay? So we need to be able to handle other types of regions. So that moves us on to the next section, section 1.16, which is non-rectangular regions. Now we'll just jump into an example and start discussing the example. So here the region of integration is on the y-axis and on the x-axis. I'm going to go between 1 and 4 on the y-axis. 4. And I'm going to go x at 0, 1, 2. So we got a couple of curves here. We got the straight line x equals 2, and we got the curve y equals x squared. And we've got the curve y equals 1. Okay, so we got these three curves, the two straight lines, y equals 1, x equals 2, and the curve y equals x squared. And the region of integration here is the region that's bounded by these three curves. Okay, so this is our region R. So we've got the function f of xy, which when we need it is 4x cubed plus 4y cubed. And the region R is the region bounded by these three curves, x equals 2, y equals 1, and y equals x squared. So the task is to do the double integral over R of f of xy dx dy. To do this thing. Now we'd like to ape what we've previously done with the rectangular regions. So we'd like to express this as some kind of repeated integral. We'll bring in the 4x cubed plus 4y cubed when we need it. But for the moment, it's not so important. So the question is now, what are these limits of integration? Well, it's not a rectangle anymore. It's got two straight sides, and it's got this one curved side, y equals x squared. So it's not quite a triangle. Well, we want to integrate over the region R. Okay. So the way we determine the limits is we generally work from the outside in. And in order to integrate over this region R, we need to integrate from y equals 1 up to 4. Okay, because this region R is contained within this band, this infinite horizontal band of the plane, which is between y equals 1 and y equals 4. But for a typical y value in this range, we only want to integrate over this small portion of x values. We only want to integrate over those x values, this little bit of the x interval here, which are all the x points for which the point x and this particular y is inside the region. Okay? And you kind of have to simultaneously consider all such possible values of y. But you see, these horizontal strips that go across the region, they always end on the value 2. You always integrate up to x equals 2, but the value of x that you start at depends on the precise value of y. Okay? The value of x that you start at is the value of y, is the value of x that lies exactly underneath the point on this boundary curve of the region. So what is this x value down here? Well, it's the x value that gives you y out of here. Okay? So this is the square root of, that's the square root of y. Okay? So our lower limit, is the square root of y on the x interval. Okay? So when we see this feature, when you're looking at one of these repeated integrals, and when you see variable limits of integration, okay, these three are constant, but when one or more of the limits of integration are variables, then you recognize you're not dealing with a rectangular region, okay? Because rectangular regions, the limits for the two variables are always the same, no matter whereabouts in the region you are, because they're rectangles that are aligned with the coordinate axis. Okay? So this is how this function is integrated over this region. Remember, the inner integral represents the integral of this function from this value of x up to this value. So the inner integral is itself going to be a function of y. It depends on the value of y. For values of y close to 1, we're integrating over a relatively long interval of x values. For values of y close to 4, we're integrating over a relatively short interval of x values. Okay. And the interpretation of this integral, just like we said in the last lecture, is the area of the curtain that lies, of the two-dimensional sheet that lies above that line, is bounded by this line in the ground xy plane, and whose top surface, or whose top boundary, is provided by the surface. And this integral represents the area of that curtain. And then we get the volume of the whole portion of three-dimensional space lying over this region by pushing this area, this kind of cross-sectional area, from this end of the volume all the way up to the top end. And that pushing, that summing those cross-sectional areas is done by the y integral. And the evaluation of the area of the cross-section is done by the x integral in the center. So having decided on those limits, we can now perform the integral as normal, and we just run with the idea that the lower limit of the integration of the x integration is a function of y itself. Okay, so we leave the y integral as it is on the outside, and we perform the x integral. So integrating with respect to x, we get x to the power 4 plus 4xy cubed. And we have these upper and lower limits for the x. After the x integration of x equals square root of y and x equals 2. I add in the x equals here to just remind myself that these are limits for the x variable. Okay. Sometimes people, after they've done one of the integrals, they end up substituting sometimes they substitute the limits in for all the variables or the wrong variables there. So it's sometimes good to remind yourself which variable these limits are attached to. These limits are attached to the x variable. Okay. Because they represent these limits on the x-axis underneath a cross-section of the area. Okay. Cross-section of the region parallel to the x-axis. That's located at a particular value of y. So we can do this evaluation now. This is integral 1 to 4. Putting in x equals 2, you get 16, 2 to the power 4, plus 8y cubed, I think. And then we're subtracting square root of y to the 4, so that's y squared, plus 4 root of y times root of 3. So that's plus 4 times y to the 3 plus a half, 3 is 6 halves, so that's y to the 7 over 2 dy, I believe. So, as expected, or as we kind of foretold, the x integral came out as being this polynomial in y. The value of the x integral was a function of y. And that was what we expected. Remember, the interpretation we gave last time was that this inner integral with respect to x is the area when you take a slice down through the volume, or a cross-section of the volume parallel to the x-axis. But it's located at a particular value of y. And so the size of the cross-section varies as you move from y equals 1 up through y equals 4. To get very close to y equals 4, you've got these tiny little, extremely narrow cross-sections.
Sorry, that 4y to 7 over 2, should that be negative?
Oh, should be, yeah, because we're subtracting it. Yeah, thanks. Go. Yeah, because we're subtracting except the lower valuation. So we got that polynomial there. Oh, it's correct in the notes. We have this polynomial here because the x integral is a function of y. Okay. The size of this cross-sectional area varies as we move along the y-axis. Okay, so it's to be expected that it's a function of y. But now, to continue the evaluation, well, we just have an integral with respect to y of a polynomial function. Okay, so we can just proceed with our standard techniques of integration. So this will integrate to 16y plus 2y to the 4 minus y cubed over 3 minus 4y to the 9 over 2, and then divided by 9 over 2, which is to multiply by 2 over 9, isn't it? Yep. And this all gets evaluated at 1 and 4, limits for the y I wanted to sit here for half an hour and watch me work that out, could, but the answer would appear to be 745 over 9. Over 9, because we got a 9 in the denominator here. That survives. Okay, but it's just straightforward arithmetic to evaluate that. Okay, but equally well, we could perform this integral where the integrals are performed in the opposite order, okay? So what about changing the order of integration here? Well, it's not so straightforward as in the rectangular case. So to just quickly repeat the diagram here, we had 1, 2, 1, 4. If I want to instead do the integral over r of f of xy, but now have y as the inner integral and x as the outer integral, expressed like this, it still represents exactly the same thing. The value of this integral is just like we defined it in the last lecture. It's the volume lying over this region underneath the surface, okay, that portion of R3. That definition of the integral doesn't depend on any preference for y done first and then x second or vice versa. But to actually evaluate it, to evaluate it as a repeated integral, we just have to make a decision about which integral is going to be the inner one, which integral is going to be the outer one. Okay? But when we present it like this, that it's the y integral inside the x integral, it isn't so easy as in the rectangular case. In the rectangular case, we simply picked up the two operations and flipped them, turned them inside out. Okay? Well, in principle, we do the same thing here, but the limits are liable to change. Okay? The limits of integration are liable to change. The reason is because we now have to look at this non-rectangular integral, take our broadest look at it, and ask ourselves, what's going on with the x variable? Well, in terms of the x variable, we're integrating from x equals 1 up to x equals 2. Those are the range of x values that you have to integrate over in order to cover the region. So we're integrating from x from 1 up to 2. And then you imagine a typical x value here in the middle. And all x values between 1 and 2, they really behave the same. In that above a typical x value is a cross-section through the region. And they all look, they're all of the same structure. They all begin on this lower boundary of the region R, and they end on this curvy hypotenuse-like side of the region. Okay, so that's the one I'm talking about. But the other ones are these similar parallel cross sections through the region. So with our limits on the y integral, we have to describe the associated interval of y values that correspond to that x value. So we need to describe this range of y values on the y-axis. Now the y values always begin at 1, okay? Because all these cross sections share the property that they all begin on that horizontal line. So the y integral begins at 1. And it goes up to a certain height, which is the height of this point on the boundary. And remember, the boundary curve was y equals x squared. So the value of this point here on the y-axis is x squared. That's the value that lies above and across from this value x on the x-axis. So the upper limit of integration is x squared. Okay. So in principle, we have just picked up the two integration operations and flipped them inside out. But because the region is non-rectangular, it changes the look of the limits of integration. But of course, it's still describing exactly the same region of integration. Just you're describing it in a different cross-sectional way. Here you're taking cross-sections parallel to the y-axis at various values of the x variable, whereas previously we were taking cross-sections parallel to the x-axis at various values of the y variable. So this integral will evaluate to exactly the same thing. Okay. So this will evaluate to 745/9 also. Okay. So you can carry that out to confirm that for yourselves. So let's have a look at another example. I want to talk about the point 11, 0.03, and the 0.53. 1, 2, 3, 4, 5. The 0.53, the 0.11, and the 0.30. And I want to talk about the triangle. Okay, so if this is the region R, which is the triangle the triangle between these 3 points. So R is the triangle 1, 1, 5, 3, 3, 0. Sorry, that's 0, 3. 0, 3. The triangle formed by these 3 points. Okay, the function we're integrating is x times y, but that's not so important. What I want to think about here is how to describe the double integral over this region R of fxy with regard to x and y. Okay. So this should be a repeated integral. So the question, the task we have to carry out is to identify clearly what the 4 limits of integration are. Okay. So that we integrate this function over this region R. Now what we'll need to be clear on is what the boundary curves are. So the boundary curves, well, this one is the easiest one to describe. That top boundary curve is simply the line y equals 3. It's the line parallel to the y-axis, to the x-axis at height 3. The other lines are a little bit just more awkward to deal with, but you've got 2 points. So if you've got 2 points, you can always get the equation of a line. This line is y is a half x plus a half. And this line over here is y equals minus 2x plus 3. That boundary curve, and this is this boundary curve. So by just considering the straight lines between the points, we get these functional relationships between x and y, which completely describe the boundary lines. So it's possible we can fill in these limits of integration now, because when we look at this region, we have to integrate from y equals 1 up to 3 in order to capture the region R. Okay? Because we have to take cross-sectional slices of R parallel to the x-axis from height y equals 1 up to height y equals 3 in order to cover the region. And then we imagine somewhere along here a typical y value. And there's a cross-section of R at that height y. And when you think about different possible values of y, each of the cross-sections behaves in the same way. It's going between a certain limit. It's going between a certain interval of values on the x-axis, from here to here. But the lower and upper limits are always determined. Well, the lower limit is always determined by the point on this line, and the upper limit is always determined by the point on that line. So we just have to ask ourselves, what are the values of these points on the x-axis that correspond to that y value? Now, to work that out, we have to actually invert these representations here. So we did have y equals 1/2 x plus 1/2, but that's equivalent to x being 2y minus 1. Just invert the relationship. And on the other hand, the other line, y equals minus 2x plus 3, that's equivalent to saying x is what? Minus, 3 minus y over 2, something. Yeah, 3 minus y over 2. So corresponding to this value of y on the y-axis, this lower limit is 3 minus y over 2. And the upper limit is 2y minus 1. So again, we've got variable limits on the x integral, constant limits on the outer integral. So the value of this inner integral will definitely be a function of y. And you'll integrate the function, and the x's will integrate to certain features. There'll still be y variable, and then we substitute these values in for the x variable. So this introduces more y variables in. So the value of the inner integral is certainly a function of y, as expected, because the cross-section changes depending on the value of y. And then that is integrated out with the y integral afterwards. Okay? So I'll leave you with another exercise, which is to what do the limits look like when we attempt to realize this integral in the other way? So when we have y as the inner integral and x as the outer integral. Okay. So that's another exercise for you to think about. Okay. And it gets slightly more complicated. Something a little else is needed. Okay, but I'll leave you to think about and investigate that.